Good morning, everybody. Thank you for joining. On behalf of the Center for Occupational and Environmental Health, I'd like to welcome you to this webinar on the topic of an overview of occupational epidemiology and the healthy worker effect, presented by Erika Garcia, who is a PhD candidate in the Division of Environmental Health Sciences at UC Berkeley. Before we begin, I'd like to just go over a few housekeeping items first. During this presentation, you'll be muted. If you'd like to ask a question, please enter it into the online chat, and at the completion of the presentation, Erika will spend 5 to 10 minutes in a Q&A where we will read your questions and we will have her expertise answering them. CE credit is available for registered nurses and may be eligible for industrial hygiene credits. If you would like to obtain CE credit and you haven't already, please register again at coehce.org, and then you will need to complete the evaluation for the webinar, and then we will email you your certificate of completion. After today, the webinar will be archived and a link will be provided available for CE credit only. Our monthly webinar series takes place on the first Wednesday of each month at 10:30 a.m. On Wednesday, April the 5th, we are very honored to be able to welcome Dr. Kent Pinkerton, who's Director for the Center for Health and the Environment and Professor in the Department of Pediatrics, School of Medicine and Veterinary Medicine at UC Davis, and he'll be presenting on climate change and health. At this time, I'm pleased to welcome our speaker for today, Erika Garcia. As I mentioned, she is a PhD candidate completing her PhD in the Division of Environmental Health Sciences at the University of California, Berkeley. Her dissertation research is focused on occupational epidemiology using data from the United Auto Workers General Motors study, which includes an occupational cohort of workers in automobile manufacturing. She has evaluated the healthy worker survivor effect in the cohort and is using the results in epidemiologic studies on exposure to metalworking fluids and cancer incidence. Prior to her doctoral studies, she earned a master's in public health from UC Berkeley and worked with the Environmental Research Group at the Cancer Prevention Institute of California until 2014. We are very honored today to have Erika Garcia present. Thank you, Erika.
Hi, everyone. Thank you, Julia, for the introduction, and thank you, everyone, for joining us today. Let me know if you cannot hear me okay. You can just send a message in the chat, and I'll make sure to either speak up or I'll fix any audio issues. So like Julia said, today I'll be presenting on occupational epidemiology. I will be doing an overview, and then I'll get into the challenge that we have with the healthy worker effect. So the roadmap for today's presentation is, first I'll get into the objectives, what I aim for you to get out of this presentation. Then I'll get into the overview of occupational epidemiology, including what is it, why is it done, and how exactly do we do it. The how portion will have two segments, one talking about exposure assessment, and the second talking about study design, so two typical study designs that are used in occupational epidemiology. And then the last section, we'll talk about the healthy worker effect. And these include two components, including the healthy hire effect and the healthy worker survivor. So what you will get out of this presentation, what I'm hoping you will get is you'll gain an understanding on the purpose of occupational epidemiology, and then also become a little bit more familiar with some exposure assessment methods that are used in this field. Then we'll get into some, and then the typical study designs that are used. And then lastly, being aware of the healthy worker effect and what it can do to these types of studies. So now we'll get into the overview of occupational epidemiology. So first, epidemiology, what is it? One way to think about it is you're trying to answer the question, who gets disease and why do they get it? See that? Oh, let me change this little pin here. Little figure, right? You're just investigating some sort of disease, some sort of outcome. Now, occupational epidemiology is asking the question, which workers get disease and is it related to workplace exposure? So here we have the three pictures. Here we have a manicurist, and you can ask the question, are workers who are exposed to chemicals more likely to get some sort of skin irritation? Here you have an underground miner, and you may be asking a question about the association between diesel exhaust and lung cancer incidence. Here in this last picture, we have a hotel housekeeper, and you may ask about the relationship between strain during certain work tasks and musculoskeletal disorders as an outcome. So why do we do it? One reason is to identify hazards. And once you've identified these hazards, you can estimate the exposure-response relationships between the hazards identified and a particular set or specific health outcome. You can also assess the adequacy of occupational standards and inform occupational policies. You can then take this information and extrapolate it to estimate the risk in the community. So exposures that may be common both in the workplace and in the community, you can use this information. So in that way, workers kind of serve as the canary in the coal mine, helping identify new hazards, and then we can put that for the community setting. So some common environmental hazards were first identified in worker populations. So soot, here we have a picture of a chimney worker, a chimney sweep. Asbestos, here we have some union members in the UK who were protesting the use of asbestos in their workplace. Lead has a long history as a hazardous thing in occupational settings. And more recently, diesel, here you have a picture of an underground miner being exposed to diesel. So why is this the case? Well, workers tend to be a well-defined population, and they also tend to have higher exposures. With these higher exposures, we are more easily able to detect an association between an exposure and a health outcome. Also, the availability of employment records and exposure monitoring records allow us to better capture the exposure information, and then you can use that to link it with the outcome. So that was the why, and now we get into the how. How do we do occupational epidemiology? Now, this is a great quote from this book, Research Methods in Occ-Epi. I use this a little bit throughout the presentation. And this says, the study designs and analytic methods used in occupational epidemiology are essentially the same as those applied in studies of disease with non-occupational causes. That is, the methods used in occupational epidemiology are the same as those used in other types of epi. So then let's ask the question, well, what does then distinguish occupational epidemiology? One of the big things is that the study population who we're examining are workers. So here are a few different workers, right? We have some garment workers in New York. Here are some roofers. Here are some custodian workers at a university. Now, some of the outcomes that are being examined in this field are uniquely occupational. So we have pneumoconiosis. So we have silicosis from silica, asbestosis from asbestos, and black lung disease from coal dust, which is depicted here. Byssinosis, or brown lung disease, depicted here from cotton dust, and bronchiolitis albiterans from diacetyl exposure. Now, this is something in food manufacturing, including popcorn. Now, other outcomes that are examined in occupational epidemiology occur both in the worker population, but also in the general population. So like cancer, asthma, heart disease. So we have workers, the study population is workers. Some outcomes are uniquely occupational, but some are not. Now, I just want to highlight this bit here about the fact that the study population is composed of workers. So we already stated that their exposure tends to be higher than in the community setting. And workers are often a highly selected population. And one way in which they are selected is that they tend to be healthier than the general population. So I think many of you have seen this photo. I think most people have. Workers on the Empire State Building in New York. Now these men here, you know, there's some selection going on. They are not representative of, they are likely not representative of all men in New York at that time. There's something different about them. So we're going to get back to this point when we talk about the healthy worker effect, but I just wanted to point it out now. So now we're going to get into exposure assessment. So in epi studies, we're usually trying to test a hypothesis. We're assessing the relationship between a particular exposure and a particular health outcome. Now, the exposure assessment is how we capture this exposure information. So if you understand the production process, this can help inform how you're going to collect data on your exposure. So let me just switch this here. So if you know workers in this area were using a particular physical agent, you would expect that workers and tasks being done here are going to have higher exposure than, let's say, workers that are in the back over here. They're less likely. They're going to have lower exposure to this particular physical agent. So understanding the process can help inform your exposure assessment. You would, at minimum, would like to be able to distinguish heavily exposed jobs from less heavily exposed jobs within a workplace. And preferably, you would want to collect some sort of quantitative data on the exposure in the workplace. And data generated by such monitoring can be used for the exposure response analysis and then also for establishing health-based exposure limits. So you need data that captures exposure. And for an exposure to exert a toxic effect, it has to reach the human body. So we have to consider the potential routes of exposure. Now these include ingestion, inhalation, and dermal contact. So there are many occupational exposures like dust and gaseous vapors that occur as airborne contaminants. So the predominant route of exposure for these would be inhalation. Of course, other routes can be important. Dermal exposure, for instance, can be an important source of important route of exposure for pesticides and solvents, and ingestion via hand-to-mouth contact can actually be quite important for lead. Now, this framework, this idea of routes of exposure, isn't necessarily applicable for all exposures. If you were looking at physical behavior for musculoskeletal disease or for injuries, this framework wouldn't quite work for there. But for physical agents, for contaminants, this often does work. Now we're going to get into a few exposure assessment tools. This is not by any means exhaustive, just a few. First thing I'm going to talk about is questionnaires. Right, here we are. Questionnaires are nice because they can be really fast and simple to implement. Some disadvantages is that workers may not be aware of to what chemicals or what physical agents they are being exposed to, or they also may not remember accurately about the past. So if you're asking about past exposure or even past jobs that they had, after a while your memory gets fuzzy. You may not remember everything. So next we have workplace monitoring. So you can sample the workplace for what your exposure of interest is. So here we have a personal monitoring in a pig farm. Here we have the lumbar motion monitoring for ergonomic assessment in a facility. Here this gentleman is monitoring noise, that's what that microphone is, in this environment. And you can also do surface wipes and skin wipes. Now, some advantages for this kind of work or this kind of tool is that you're getting quantitative exposure assessment. And it can also give you more accurate exposure information. Now, some disadvantages: you can only really do this at the time. You can't get past exposure this way unless you think that the jobs haven't changed very much in the past. They tend to take more time, they tend to cost more money, and you will have to have some knowledge about the specific equipment that you're using. So if you're using a monitor or this lumbar motion monitor, you will need to have knowledge about that and what the appropriate monitoring methods are for your target exposure. There is also biological monitoring as a tool available. Now, this is getting at the dose, what's inside the body. So you can test for solvents. You can do this in the blood, in urine, even in your breath or in the worker's breath. Metals can be assessed in hair, blood, nails. You can look at various chemicals in hemoglobin or DNA adducts. Now, this method integrates exposure that are reaching the body via different routes of exposure. So if you're breathing it in, if you're ingesting it, if you have dermal contact, this will measure all of those routes. And you're estimating the amount of the exposure that's actually taken up into the body rather than the amount that's in the surrounding environment. Now, you can view this as an advantage or disadvantage depending on your particular question that you're trying to ask. The other thing that's important for this type of monitoring is the biological half-life of what you are measuring. So time is important. Some things may stay in the body for only a few hours, some a few days, some for much longer periods of time. So again, depending on what the specific target, what the specific exposure that you're targeting, if you have something that lasts for months, maybe that's great. But if something that lasts for days, you only have a short window of time to get in there and do the assessment. Some other advantages: again, this is a quantitative measure of exposure, and disadvantages similar to the monitoring in the previous slide is costs, getting the labs to run these analyses, and also the willingness of participants to provide the samples. So some things like saliva may be easier to get, but maybe blood may be a little harder to get participants to submit that. And I do just want to take a moment to talk about the difference between dose and exposure. So exposure is the presence of a substance in the environment, right? It's outside of the subject. It's in the air, it's in the water, it's on the surface of your desk. So this can be something like lead in paint, the carbon monoxide in the air. Dose, on the other hand, is the amount of the substance that's at the biological target. And it's during some specified time interval. Again, this is going back to the biological half-life of different things that get into the body. So this would be, the blood lead level and blood carboxyhemoglobin, and these would measure these items up here. So exposure is what's outside the body, and dose is what's inside the body. So you probably have heard me say exposure response a few times during this presentation, and that's because often in occupational epidemiology, we are working with the exposure, what's outside, what's in the environment, what's in the workplace, rather than what's inside or what has reached the worker's body. Sometimes you hear dose response, but here we're using exposure response because that's what we have. Just want to make a note about that. Okay, so one can assess exposure currently or prospectively. So here's the start of the study, and you're looking at exposure now and in the future as you're moving through time. Now, all the methods, all the tools that I mentioned, the questionnaire, the workplace monitoring, the biological monitoring, are amenable to this type of time frame that you're looking at. And here's just some examples of things you may be measuring depending on what the health outcome is. Now, you can also assess past exposure. So here's the start of the study, but you're actually looking at exposure that occurred behind in the past. Now, a questionnaire is still suitable for that. You can ask about previous jobs, previous exposures, while workplace monitoring and biological monitoring may not be as helpful unless you have records. If you have records of these items, then they can be. If you have in a company, if an industrial hygienist has come in and done some workplace monitoring and there are records of those, they may be, you can use them for the exposure assessment. However, you will have to think about why they were collected and if they are truly representative of exposure in that particular job or task. Oftentimes in occupational epidemiology, you have what's called a GEM, a job exposure matrix, being created, and this is linking exposure information for particular jobs with employment records for your participants. So once you know what jobs they were working and you know what exposure levels each job had, you can then create the exposure levels for each of your participants. So this is something that's often done in occupational epidemiology. Okay, so the last thing I want to say about exposure assessment is that it's really important. You need to have accurate exposure information when you're doing occupational epidemiology. All of these methods often require some sort of expertise in them. Whether you're writing a questionnaire, you have to make sure that you are writing good questions, clear questions. And using these tools, you need to make sure you know what you're doing when you're doing them. And the same thing with biological monitoring, making sure that you're testing for the right metabolite in these different specimens or what have you. So now we're going to move into the study designs. So I'll talk about two different study designs, cohort studies and cross-sectional studies. Now for each of these, I will talk about the basic approach. I go through a simple example just to help you understand it, and then some common measures of association. So the cohort study. This is the gold standard for observational studies. Now, you may be thinking that, well, the randomized control trial, that's really the gold standard. Yes, for experimental studies, but often manipulating exposure is unfeasible or even unethical in a workplace setting. So for observational studies, the cohort study really is the gold standard. And so what we're doing here is we identify a population of workers and we follow them over time for a select health outcome. Now, at the end of the study, you estimate the risk of the disease or injury in that worker cohort. And you can also estimate the relative risk by comparing risk in the high exposed to lower or non-exposed workers. So now we're just going to go through a visual example to help you understand this if you're unfamiliar. So here is our study. We have 50 workers that are enrolled. We do the assessment for the exposure, and we have 25 that are exposed and 25 that are unexposed. So our exposed are these orange individuals, and the unexposed is the green. So here's the start of follow-up. Now we follow them in time, and at time 1, which I'm going to say they're years, so after the first year, we have some individuals that get the disease. So if an individual has this yellow little box and they've turned white, they have the disease. So in the exposed group, we have this individual and this individual. So 2 out of the 25 got the disease, which you see here, whereas 1 out of the 25 in the unexposed group got the disease. And once they have the disease, they are no longer at risk for the disease. They get it once and that's it. So they are no longer followed for the outcome. They're no longer followed in the cohort. So for the second year, you see their spaces are now missing because they already had the outcome. So they're no longer followed. Now here you have some more people who came down with the disease at year 2, year 3, and year 4. That's the end of our study. So we had 7 individuals who were diseased by the end of the study, and in the exposed group, and 4 in the unexposed group. So I just tallied that up here for easy reference. So now that we have these numbers, what are we going to do with them? So that gets into the measure of association. So it's just a miniature version of those photos, but the numbers are repeated here. So the first thing we're going to talk about is cumulative incidence. So now this is the number of new cases during follow-up, which we knew 7 here and 4 here, divided by the number of people at risk at the beginning of follow-up. So for each of these, it is 25. So this is essentially the probability of disease during the study. So to calculate the cumulative incidence in the exposed, you're going to get the number of new cases during follow-up, 7, divided by the number at risk at the beginning, 25, and that gets you 0.28. And the cumulative incidence in the unexposed is the same thing, so it's going to be the 4 over 25, and that's going to equal 0.16. Okay, so now that we have these two, numbers of cumulative incidence in each of our groups, what are we going to do? We are going to make a ratio. We're just going to put one over the other. There we are. So we're going to make the cumulative incidence ratio. So that's going to be the cumulative incidence in the exposed. That's the cumulative incidence in the exposed divided by the cumulative incidence in the unexposed. So that's 0.28 divided by 0.16. Here, remember, the unexposed is a referent group. That's who we are referring to. And so this is going to give us an incidence rate ratio of 1.75. So the cumulative incidence ratio of 1.75. Now, the cumulative incidence ratio is sometimes called the risk ratio because the cumulative incidence is the risk. So cumulative incidence ratio of 1.75. Now, what does this number mean? So I'm going to take a little moment here to talk about relative measures of association, especially for those who are unfamiliar with it. So relative measures of association, they're a ratio. It's one number over another number. And so here in the cumulative incidence ratio, we had the risk in the exposed divided by the risk in the unexposed. So if the number is the same, so if that risk is the same in both groups, your number is going to be 1, which means there's no association between the exposure and the outcome. You have the same risk in one group compared to the other. So 1, that means null, nothing. No association. Now, if instead the risk is higher in your exposed group, so the number in your numerator is higher than the number in your denominator, you're going to get something above 1. And so if it's above 1, it's harmful, right? Your risk is higher in your exposed group than in your unexposed group. Now, if instead the number in the numerator in the exposed group was lower than the number in the unexposed group, it means that the exposure is protective. It's reducing the risk. So 1, if it's below 1 and it can approach 0, it's protective. And if it's above 1 and it approaches infinity, it's harmful. So these measures of association indicate both the direction, protective or harmful, but also the magnitude of the association, the strength of the association. So the higher the number it is, the more harmful it is. The lower the number it is, the more protective. So here's just some example interpretations. So for a cumulative incidence ratio of 1.75, it means that the risk of the outcome in the exposed workers is 1.75 times the risk of the outcome in the unexposed workers. So if you're timing something by something that's higher than 1, it's going to be higher. Now, if instead you had a CIR of 0.5, then the risk of the outcome in the exposed worker is 1.5 times, or half, the risk of the outcome in the unexposed workers, right? So it's protective. It's half the risk. Okay, so now we're going to get back to measures of association in cohort studies. So we talked about cumulative incidence and cumulative incidence ratios. Now we're going to talk about incidence rate. So this is a number of new cases during follow-up, so the same numerator, but now we're dividing by the total number of person time followed. Now, you may be asking, well, what's person time? Person time is just a unit. We're going to use person years because we follow them for 1, 2, 3, 4 years. And what a person year is following one person for 1 year. It's analogous to pack years if that's something that you're familiar with. So now if you had 100 person years, you could have followed 10 people for 10 years, 20 people for 5 years, 25 people for 4 years, right? It's gonna multiply out to 100 person years. So, and this is the rate of the disease during the study. And what this takes into account is the fact that you did not follow 25 people for 4 full years. You'd followed 25 people the first year for your exposed, 23 for that second year, 22 for the third year, etc. So you take into account that you have different denominators in each year. You have different number of people that are being followed over time between your exposed and your unexposed group. And so now we're going to calculate the incidence rate in the exposed. So it's the number of new cases during follow-up, which you know is 7. So 7. But now we're going to do total person time. So we're going to add up the 25, 23, 22, and 20. That's going to give us 90. So we had 90 person years of follow-up in our exposed. And that's going to give us 0.078 cases per person year. You can also multiply this out. So say if you want to do it per 100 person years as opposed to just 1 person year, you just multiply both pieces. So this would be 7.8 cases per 100 person year. So that you would expect 7.8 cases if you follow 10 people for 10 years. Now the incidence rate in the unexposed group, same formula, 4 over, and then you add in the 25, 24, 23, 22. And that gives us 94. So you can see we actually had a little bit more person time in the unexposed group compared to the exposed group. And so that just this measure takes that into account. So we get 0.043 cases per person year. Now what do we do with these numbers? We make a ratio. So we make the incidence rate ratio, which is the incidence rate in the exposed divided by the incidence rate in the unexposed. So again, the unexposed is our denominator. It's our reference group. You do the math, and you get 1.83. Now, again, you interpret this the same way as the previous measure, except using rate instead of risk when you talk about it. But it's above 1, so it's harmful. The exposure is associated with higher disease, more disease. Now, the incidence rate ratio is sometimes just called a rate ratio. So sometimes you'll hear just rate ratio, and that's what this is referring to. Okay, so that is the bit about cohort studies. And now we're going to get into cross-sectional studies. So the basic approach is that it kind of captures a snapshot of the workers at one point in time. And you're usually assessing the exposure and the health outcome at that one point in time. And you are comparing the prevalence of a select health outcome or outcomes between different workers of varying exposure levels. Now, this is especially suitable for non-fatal diseases, symptoms, and other kind of physiological variability, right? Something that stays with the person rather than something that happens at one point in time. So I do want to talk a little bit about prevalence. So prevalence is the proportion of individuals who have a disease or a condition at a particular time. And this includes both, prevalence includes both incidence and disease duration. So here is just a little bit here where we have 12 workers over time. So here's time moving along. And over time, they go into these disease states. So here, if they're in the red, they have the disease, and then they recover, and they're white again. And some people never get the disease, and some people do. So if we came in and did one snapshot in time, and we're just going to do the midpoint here, we would say that the prevalence is 3 out of 12, because 3 workers have the disease state out of the 12. Now, if instead our disease duration was a little shorter, so the incidence remains the same, right? We still have the same 1, 2, 3, 4, 5, 6, 7 individuals who got the disease. See the same people, but the disease duration is just shorter. I just made them a little shorter. And we're doing the exact same assessment right in the middle, but now we only capture one individual. We only have one person who has the disease state at this point in time. So although we didn't change the incidence, we changed the disease duration, and so that made our prevalence go down. So if you have a situation where you have both diseases with long disease duration and then you have some with shorter disease duration, you are more likely to capture those subjects with longer disease, and you're less likely to capture those with shorter disease. And so this can be very important if there's something different between the shorter disease durations and then the disease with the longer disease duration. So if this kind is more severe and you're less likely to capture it, maybe you're underestimating it. And if this is more severe, maybe you're overestimating it if they're associated with a longer disease duration. So that's just something to keep in mind about prevalence and about cross-sectional studies. Okay, so now we're going to go through the simple example of a cross-sectional study. So here we have a workplace. There are 20 workers, 10 of which are exposed, 10 of which are unexposed, and time. So here's over time, they get into this disease state, and then they recover, and they're healthy again all throughout. That's what these little red lines are. So a disease state, and then they recover. So this is what is happening. We don't observe this. This is just what I'm saying is happening in this particular facility over time. Now, what we do is we come in at one point in time and we do an assessment. We come in here at the midpoint and we assess their exposure. We say, okay, you guys are the exposed and you individuals are the unexposed, you're unexposed, and then we assess the outcome. You see this individual has the outcome, but the others don't, and these two do. So we don't see everything, just see the one snapshot, this one-time survey. So I'm just going to move them over. It's the same bit. I've just moved it over to the left here. So now we're going to calculate prevalence. So this is our measure of association for cross-sectional studies. And this is the number with the disease divided by the total number of subjects. And so it's essentially the proportion of subjects with disease. So we're going to do this for the exposed group. And you have 2 out of the 10, so 0.2. The prevalence in the unexposed group, you got 1 out of 10, so 0.1. And similar to the other measures of associations, we're going to do a ratio here. So the 0.2 divided by 0.1, again, the exposed group is in the numerator, and the unexposed group is in the denominator. That's who we're comparing against. That's the reference group. And we get a prevalence ratio of 0.2. Again, you interpret it the same way as the other relative measures of association. It's above 1, so the exposure is harmful. So you can say that the prevalence of the outcome in the exposed group is 2 times or twice that of the unexposed group. And then one last thing I want to say about cross-sectional studies, and that's the issue of temporality. So here is that big picture that we didn't observe. We just did that one snapshot, and we have people going in and out of disease states, and this is when they were hired. So they were hired here, and some of them get the outcome, some of them don't. So if we had instead taken this snapshot here, this worker would be counted as having the disease and being exposed. But what we don't know is that the worker actually had the outcome before they were even exposed. So here, let's see if I can get this pin to work. This individual was actually sick before, had the disease outcome before they entered the workplace. So they had the outcome before they were exposed. So the exposure cannot cause something that happened in the past. But because we just did, there we go, the one snapshot, we didn't realize this person already had the outcome. And this is something, it's a little bit more difficult to assess temporality, knowing that the exposure came before the outcome in a cross-sectional study. So it's just a little harder to do that, especially when the disease is something that people don't know they have until you do the assessment. Okay. So now we're going to get into the last section, the healthy worker effect. So we're getting back to this point that our study population is comprised of workers and that they are more selected than the general population. And one way is that they are healthier than the general population. So the healthy worker effect, this is that workers typically have a lower overall mortality rate than the general population. So healthy individuals are more likely to be hired, and they're more likely to remain employed. Some components of the healthy worker effect include the healthy hire effect and the healthy worker survivor effect. So this relates to, the healthy hire relates to the first point, and the healthy worker survivor effect relates to the second point. So we're going to take these each in turn. The healthy hire effect. So it's the initial selection process whereby healthy individuals are more likely to seek and gain employment than those who are relatively less healthy. And there we go. So here's just a visual depiction of that. So here's the general population. You have a mix of people. And so these colors indicate more healthy versus less healthy individuals. So if they're more green, they have a better health status. And if they're more red, they have a lower health status. And you have just an average individual here. And so your worker population just tends to be more healthy. You do have some individuals who have, more red, like here's one, here's another, but it's not representative of the general population. They tend to be more green. They tend to be more healthy. And you can think about how this effect can be stronger, that there's more selection in more physically demanding jobs like firefighter and construction. So the healthy hire effect is a concern when you're making a comparison of an occupational population with an external reference population like the general population, because their mortality rates are going to be higher. So there was a measure of association that was more commonly used in the past called standardized mortality ratios, or SMRs. And these compare the mortality rates in a worker population to the U.S. general population. And that measure was problematic because of the healthy hire effect. Because, like I said, workers have a lower mortality rate than the general population. So the effect, if the exposure in the workplace is harmful and it's increasing the mortality in your worker population, but workers already have a lower mortality to begin with, it can mask the effect. You may not see that association between the exposure and increased mortality, or it may look something that's really harmful, may make it look a little bit less harmful than it truly is. And so how you avoid the healthy hire effect is, instead of using the general population, instead of using SMRs, is to use an internal reference group of workers. So use workers within your same facility, within your same plant that had no exposure or low exposure. And this is what we did in our examples. Okay, so now we're going to move on to the healthy worker survivor effect. And so this is that less healthy workers preferentially leave the workforce, resulting in a survivor population of workers that remain at work. Right? If you're less healthy, you're more likely to leave work, and those who stay on the longest or longer tend to be healthier. They survive work, hence the healthy worker survivor effect. So again, another visual here. So here is our worker population, and this is just the same picture that I used in the healthy hire slide. They're a little bit more green, but you still have some mix of folks. At year one, people leave work. That's just how it goes. But the red people who are on the more red side tend to leave quicker than those that are on the more green side. And here's year 2, year 3. So at the end of year 3, you're looking more green than when you started. And so your population is just getting healthier on average over time. Now, the people who leave, they can be leaving the workforce completely. They can be transferring to lower exposed jobs. And you can think about how this effect, again, would be maybe stronger in higher exposed jobs and more physically demanding jobs. So this is the healthy worker effect, that you have people who leave earlier, people who have less exposure, are also less healthy compared to those who stay on longer. They tend to be more healthy. So people who have the most exposure, you've stayed on for 3 years, you also have the better health status. So people who stay on longer, better health status, and also higher exposure. People who leave earlier, lower exposure, and also lower health status. So now we're going to walk through an example to demonstrate the impact of the healthy worker effect. So in order to do this, we have to gather some exposure information, and we're going to use years of work as our exposure. So first we need to know who remained employed. So here's the distribution of who we had in each of these categories over time. Here's hire, year 1, year 2, year 3. And we're just going to calculate who left at what point, how many people left at each of these time points. So just taking these numbers, and I know there's a lot of numbers on this slide, but we're going to go through them slowly and together. So here's those same numbers that I had on the previous slide. So we start out with 70 people. 11 of them left during that first year. And so those 11 people, their years of exposure are now 0 to 1 years. And this is just the distribution. So for here, we lost 3 people. 3 people left. So now they're in this cell. And the next year we lost 9 people left. So they're here, again, the distribution, and this goes all the way through. And we ended with 43 individuals at year 3. So the people who have 3 or more years of exposure is 43. And again, this is just, so here we had 3 people leave, so that's the 3. Here we had 2 people leave, that's the 2. So this is just the number of people in this exposure category. And now we're going to further categorize it into if you had less than or equal to 2 years of exposure or greater than 2 years of exposure. So 9 and 11 is 20, 7 and 43 is 50. So we're just categorizing exposure, and we're using this kind of cumulative measure of exposure as years of exposure for our measure. And again, the cumulative exposure is important because employees who leave are accruing less exposure than their counterparts who remain on the job. So now we're just going to assume for this example that the risk in the workers that were exposed less than 2 years is 20%, and the risk in the workers exposed more than 2 years is 23%. Now these are just numbers that I came up with, so you can take these as the capital T truths that I am telling you to work through this example. So don't worry about the numbers too much, just I made them up, go through the example. So 20% for the low exposed group, 23% for the high exposed group. This would be cumulative incidence. So you had 20 people in this group, 50 people in this group. Your expected cases, you would just multiply the total people by your percentage. You would expect 4 cases during the follow-up period in this group, 11.5 cases in the high exposed group. I know there's a decimal there, just bear with me. If it makes it easier, you can think of this as 200 and 500, and this would be 40 and 111. But your expected risk ratio would be your risk in your exposed group or your high exposed group divided by your risk in your low exposed group. This is 1.2. So the exposure is harmful. But now we also know that people have this different susceptibility depending on their health status. So if they're more healthy, they're less susceptible to the exposure for the outcome. And if they're less healthy, they're more susceptible. And these are numbers that I'm just providing to work through the example. So on average, we still have the 20% and the 23% for your low and high exposure groups. But if you were in this category, instead, if you were more healthy, you actually had 30% less risk, so you have 14% of 20. And if you're in the less healthy group, here, if you're in the red group, you actually have 30% more chance. So instead of 20%, you have 26%. These are the numbers just fill in. The same thing for your high exposed group. Here's your 23% for everyone on average. But if you are the healthier people, you actually only have about 16%. And if you are less healthy, you have almost about 30%. So this difference in susceptibility is not inherently a problem. It's okay. But it's an issue if the distribution of your susceptibility is different in your different exposure groups. So if this is the same between your high exposed and your low exposed group, the number of people in each of these cells, then you're okay. But if they're not, that's when it's problematic. And because of the healthy worker effect, it isn't. So here, we're just bringing in those numbers again of how many individuals by this health status were each of these groups. So you still have 20 overall and 50 overall in your low and your high groups. But now you're seeing the distribution as to which health status group they were in, how healthy they were. So you see the distribution in your low exposed group, you have someone in every cell, they're a little higher in the middle. Now if you compare that to your high exposed group, to those that were exposed 2 or more years, or 2 years or more, they tend to be skewed on the more healthy side, right? You don't have anyone in this red cell, and they're really all up here. So because of this difference, this is going to affect your results. So I'm just doing a weighted average here. So this is just taking the numbers, the distribution here with their exposure, with their risk level, just multiplying them out, dividing them by 20. And so the average risk here is 20.6%. The same thing with this group. So that's not too bad because it's 20%. So 20.6 a little bit higher, but not so much. Now for this group, I did the same thing, right? Taking this distribution and these percentages for the 50 individual, and instead of the 23%, I'm getting 19.5%. And that's because we just have a lot more healthy people, and so instead of getting this 23%, we're getting more of these 16 and 20%. So it's really bringing down the average risk. So this group now we have 16.5%. You can do the expected number of cases given these risks. So 4.1 compared to 4 before, and 9.7 compared to 11.5. So that's actually quite lower. So now your risk ratio, you just divide the risk in the exposed group divided by the low exposed group. And so now our risk ratio, earlier it was 1.2, and now we're getting 0.9. So the effect of the strength of the healthy worker effect is so high that we're actually not just masking the association, so we're not just getting to 1, we're actually going below 1. It's a downward bias, and now it looks like the exposure is protective. And so this is the issue with the healthy worker effect. Your high exposed group are also more healthy. They're less likely to get the disease, and so when you make the comparison, it can look that staying at work and being exposed actually decreases your chance of the outcome. And it's not so much that the exposure does, it's the fact that you were able to stay at work for that long. So the healthy worker effect, if you do not properly take it into account, when you're doing your analysis, your results will be biased. And a bias, again, is just the systematic deviation of the results from the truth. So the truth is here, this is where we should be, but instead we're kind of being pushed off to one side. This differs from like random error and precision issues. This is like an accuracy issue. We're actually being pushed off to the side. The methods to control for the healthy worker effect are a bit complex, so I think at this point it's just best to be aware of this potential source of bias when you're reading or even conducting occupational epidemiologies. And this is true for both the healthy worker survivor effect and the healthy hire effect. Great, and then lastly, I'm just going to end with some additional resources. So a great book, if you're interested more in the methods for occupational epidemiology, is this Checkaway book. If you're interested just generally in epi, this Shorter-Rothman book here. If you're interested more in the healthy worker effect, there's these great papers here that go into it, including the healthy worker survivor effect and different methods that are available to control it. So thank you very much, everyone. I guess we'll do the Q&A now, and if there's any questions that are not answered during the Q&A session, or you just want to get in contact with me, here's my email address. Please feel free to shoot me an email. Thank you.
Erika, thank you so much for that presentation. I found it so helpful to be able to be a better consumer of research studies too. It was very good. We have a couple of questions, and hopefully please do enter any questions you have into the chat section. We'll spend about the next 5 minutes on Q&A. The first question we had was for the cohort study. The participant asked, how long do you usually follow participants in a cohort study?
Yes, that's a great question. It really depends on what the outcome is that you're looking at. So here, just going to pop this up here. In my little trivial example, we followed them for only 4 years. If you have something that has a high incidence, the higher the incidence, the less amount of time you need to follow them for, right? Because you're going to pick up enough cases within a shorter period of time. Now, something with really low incidence, you would need a longer period of time to follow them because you need to have sufficient number of cases to have a power to detect an association between the exposure and the outcome. Now, if your incidence is really low, say if it's if it's really low, cohort studies are not, a prospective cohort study at least, is not the appropriate method, or may not be the appropriate method to use, or the appropriate study design to use, because you're going to have to wait a really long time to have a sufficient number of cases, and there are other study designs that may be more appropriate. Cohort studies are also quite costly, so that has to be taken into account as well. So sometimes how long you follow a population for may be dictated by how big your budget is, unfortunately. Now there is prospective cohort study, which kind of is like the one in my example that you start at the beginning of time and you follow them forward. There is also another type of cohort study called a retrospective cohort study, where instead you enumerate the people at one point in time and you kind of work backwards to see what they were exposed to in the past and when they got the outcome. So instead you kind of start on this end and you work backwards, and that may be more appropriate for something that has a longer a time for, or lower incidence, or something that takes a little bit longer to develop as a disease.
So it sounds like it's important in the study design to know the disease that you're going to look at and its severity and frequency.
Yes, yes, very much so.
Another question, again, I think in relation to the cohort study, is what happens if study subjects die during the study period? Are they removed from the study?
Yes, so generally, yes, when you have a subject who passes away, they are removed for your study because they are no longer eligible for the outcome. You follow someone until they are eligible for the outcome. So if you're studying something like, let's say, incidence of incidence of a cancer, and someone has passed away, then they are no longer eligible for the outcome. They cannot get cancer when they have passed away, so you don't follow them in time anymore. What you do is you actually censor them, which means they kind of drop out like these people do, where you don't follow them. They're just kind of this empty little section, but they never got the disease. We just follow them up to a certain point in time. Up to that time, they hadn't gotten the disease, but then we no longer follow them. And so that's something actually I didn't bring into this example because I wanted to kind of present something simple. But yes, you also have censoring due to death, due to, depending if it's something that you're using a state systems. If they leave the state, they won't be there. Sometimes even if you're looking at, let's say, ovarian cancer, and a woman has a procedure to remove her ovaries, then she knows no longer eligible for the outcome. So at that point in time, she would also be removed for the study because she cannot get the outcome. She's not at risk for it because she doesn't have the appropriate organs anymore to get that particular outcome that you're looking at for your study.
Very good. Well, thank you. That helped to explain those couple of questions. We don't have any more questions at this time, unless if anybody would like to ask something. We have a couple of minutes left. But otherwise, I would like to say thank you so much to our presenter today for a really interesting overview. We will have this recorded, and if you are interested in taking a continuing education credit, it would be available to you. Please feel free to email us if you have any questions after this event, and we really appreciate your taking the time to complete the evaluation. The link was included in the email you have received for this webinar confirming your registration. Again, next month on April 5th at 10:30 a.m., we will be having Dr. Pinkerton from the director of the Center for Health and the Environment at UC Davis, who will be presenting to us about climate change and health, which should be really interesting too. So please join us then, and thank you very, very much for spending your time with us this morning, and thank you to our presenter, Erika Garcia.
Thank you very much, everyone.
Thank you. Goodbye.